Hi, welcome to Mathematics for Machine Learning. We've already looked at maximum likelihood estimation as a method to find the parameters of a statistical model. It worked by introducing a probability distribution on the observed data that depends on our model, and then maximizing this probability distribution, the so-called likelihood, over all the parameters of the model. The parameters then are the so-called maximum likelihood estimates. We have tried this out in the context of the normal distribution to find the mean and the variance estimates. We found that the maximum likelihood estimates correspond to the sample mean and the sample variance. Today, we will look at a Bayesian way to find model parameters. And again, we'll use the normal distribution as an example. So the maximum likelihood estimates of the normal distributions are the sample mean and the sample variance. So they are quite intuitive. Namely, the sample mean is just the average over all our data points. So the samples that we observe. And the sample variance is the average squared deviation of these points from this sample mean. Now, we have already identified some problems with the sample variance. And in the literature, the bias-corrected sample variance has been introduced, that instead of dividing by n, the number of data points, divides by n-1 in order to account for the fact that we're using the data somehow twice. Once to estimate the mean, and then using this estimated mean to estimate the variance. Today, we will look at Bayesian methods to fix this problem. Well, but let's quickly actually look at the problem. Well, it starts already if we had only a single data point. Yeah? In the case of a single data point, well, the mean would be just this data point itself. So it's 1 divided by 1. The sum over all these data points is just one data point, right? So it's itself. However, if we use this to compute the sample variance, we would in effect compute x1 minus x1 and square that. So we would compute a 0, square a 0, and the variance estimate, the maximum likelihood estimate, would be 0. Now, it's quite clear that this is a value that is too small. Maximum likelihood estimation is a so-called frequentist method. This stands in contrast to a second statistical school, namely the Bayesian methods. So the key difference with Bayesian methods is that Bayesians would treat all the unknown parameters of a model as random variables themselves. Just assume that they are known. Say we had a linear regression where we say that, well, y is x, the input, times a weight plus another weight. Then we have two unknown parameters of this linear regression models. And the Bayesians would treat these as random variables that are unknown. Random variables have a distribution, and the distribution of these parameters is what we're after. That's exactly what we want to learn. And we want to learn this distribution given the data, given our data set. So in this case, the data set is fixed and the parameters are unknown and a random quantity. Now, we might already know something about these parameters. For example, we could say, well, we could identify sensible value ranges. For example, on our linear regression models, we could say, well, we don't want these parameters to be too large in magnitude. So if we had extremely large positive or negative values here, we get functions that are quite extreme, which we typically get from overfitting, right? And this knowledge that we want somehow, for example, relatively small in magnitude values, we put into our prior distribution. So the prior distribution formalizes all our assumptions on the parameters, all our prior knowledge of these parameters. And what we're after is to take this prior distribution, combine it with the likelihood. The likelihood is the same thing as we have seen with maximum likelihood estimation. It's a model of the data. It models the probability of the data under our model with all our parameters that we put into that model. What we're after is the distribution of the parameters given the data. It's a conditional distribution. The posterior distribution is obtained by applying Bayes' rule. So it's P of theta given D is equal to P of D, the data given theta, that's our likelihood, times P of theta, that's our prior. And then we take this product and divide it by P of D. And P of D is a marginal distribution of the data, where we marginalize over all possible parameter values. Now, you can think of this P of D as a normalizing constant. It basically takes the product of the likelihood and the prior and makes sure that it integrates to 1. Now, how can we work with this posterior distribution? Well, we could, of course, do something similar to what we did before in the frequentist setting, where we maximize the likelihood. Now, instead of maximizing the likelihood, we have the posterior distribution. Let's look at this and maximize the posterior distribution. And that actually is a very common inference technique that is known as maximum a posteriori estimation, or MAP estimation. We said that our parameters are random variables with prior P of theta. Now the posterior distribution is given by Bayes' rule. So say we have n IID data points, then P of theta, conditioned on all of these data points, that's our posterior, is proportional to the prior times the likelihood, so the probability of this data, given this parameter. Now the normalizing constant we left out. Instead we wrote proportional, which means that they're equal up to a multiplicative constant. And this multiplicative constant is this normalizing constant that we talked about just before, the probability of the data, the marginal probability of the data. The problem with it is that it is typically intractable, because it requires to take all possible configurations of theta into account, which typically is done by solving some very high dimensional integrals or very large sums. As long as we only want to maximize the posterior distribution, then this is actually not a problem. We don't need this constant, which is so expensive to compute, because we have something that is proportional. So it's equal up to a constant. It's a constant that does not depend on the parameter of interest. So the proportional part, here's the product of the prior times the likelihood, should have the same maximum. And that's exactly the trick that we do in maximum a posteriori estimation. We maximize the product of the likelihood and the prior, or equivalently, typically it's just mathematically a little bit easier to take the log of that and maximize the log. It will have the same optimum theta hat. Of course, for IID observations, So if all our x1 through xn are sampled identically, so from the same distribution, from the same likelihood, and independent of each other, identically and independently distributed, then the map estimate is the argmax of a log prior plus the sum over the log likelihoods of all of these data points where these are all identical distributions. Let's look at an example. Say we want to estimate the probability of flipping heads with a coin. Typically this is modeled using a Bernoulli distribution where the probability of heads is just given by some parameter theta that goes from 0 to 1. On a fair coin, theta would be 0.5, where heads is equally likely than tails, which the probability of tails, of course, is 1 minus theta. Now say we have 3 samples. We have heads, and tails. Then the likelihood would be the probability of heads to the power of 2. We have twice gotten heads, times the probability of tails, which is given by 1 minus theta, to the power of the number of times we got tails, which is in this case 1. So that's our likelihood. To do Bayesian inference, we also need a suitable prior distribution. For a Bernoulli likelihood, we could of course use a simple uniform prior, but a very frequently observed prior distribution for Bernoulli is the so-called beta distribution. Here we see a few examples of beta distributions. So the beta distribution has a value range from 0 to 1, as our parameter theta also has. And it has 2 parameters, parameter alpha and beta. If they're both identical and equal to a value that is smaller than 1, then we see it's very peaked close to the extremes, to 1 or to 0. And we put less density to values that are sort of in the middle. If we make alpha larger than beta, then we see that we are tilting to values close to 1. If we make beta larger than alpha, then we are tilting towards values that are close to 0, like this green line here. Now, in our example, we do not have a preference because we don't know anything about this coin. So we want to make alpha and beta equal to each other. And of course, we know that many coins, they're typically relatively fair. So we should get values, put a lot of probability density on values that are close to 0.5, which would be the probability of heads for a fair coin. Of course, no coin is perfectly fair, so we put a lot of probability mass around that, and that we get, for example, by this beta distribution that has here alpha equals 2 and beta equals 2. That's exactly the one that we will use in our example. So let's compute the maximum a posteriori estimate using this beta distribution, so the beta 2, 2. The prior distribution is given by this beta, which has the form of theta to the power of alpha, where alpha in our case is 2, times 1 minus theta to the power of beta, which again said in our example is 2 minus 1, divided by b of alpha beta. And this b here is the so-called beta function. The beta distribution is a distribution, and it makes sense that this here needs to be integrated. If we divide by the integral of what we see on the top, then we have ensured that the beta distribution integrates to 1. Now, here's an ugly integral, but we will see that we actually won't have to deal with it. So if we write down the posterior, p of theta given the data, that is proportional to the likelihood p of the data given theta times the prior. And that again is proportional to, now we're leaving away all the parts that do not depend on theta. So it's proportional to theta squared times 1 minus theta. That's our likelihood. Times the top part of our prior. So we left out the normalizing constant of our prior because the normalizing constant does not depend on theta because it integrates over theta, over the whole value range. Now, if we multiply this out, we see that we have theta to the power of 2 minus 1, theta to the power of 1 times theta, that's theta to the cubed, and 1 minus theta to the power of 1 times 1 minus theta to the power of 2 minus 1, which is also 1. So we get 1 minus theta to the power of 2. It is easier to work with the log of the posterior. Now the log of the posterior is equal to some constant that we are not interested in, but that's given by, we twice found something that is proportional to the posterior. Now proportional means that we have a multiplicative constant. Now if we take the log, we get an additive constant instead of the multiplicative constant, plus the log of this term here. Now that of course we can compute. It's 3 log theta plus 2 times log of 1 minus theta. Exponents become multiplicative constants. Now we want to maximize that. The recipe, very simple. We take the derivative of this term here with respect to theta. So we get the derivative of 3 log theta plus 2 log 1 minus theta with respect to theta. If we take the derivative of these two terms, well, the first one, we get 3 times the derivative of the logarithm is 1 divided by theta. So we get 3 divided by theta. Then here on the second term, it's in a similar way 2 times the derivative of that. And here we have to be careful because theta appears here by the minus 1. So it's the derivative of the inner part, which is 1 divided by 1 minus theta. And then we have to multiply by the derivative of the inner part, which is minus 1. So we get a negative sign here. So we get in total 3 divided by theta minus 2 divided by 1 minus theta. That we set to 0 in order to get our map estimate. Well, we can quickly do that. 3 divided by theta minus 2 divided by 1 minus theta equals 0. Equivalently, we can multiply both sides by theta times 1 minus theta to put it on top. The right side still stays 0 from this multiplication. And we have to, of course, be careful that theta shouldn't be equal to 0 or 1. Otherwise, this wouldn't work here. And then the left part becomes 1 minus theta times 3 minus theta times 2 equals 0. Now we apply these things out. So 3 minus 3 theta minus 2 theta equals 0, which means that 5 theta equals 3, or theta equals 3 divided by 5. That's our map estimate. Now, it is interesting to note that if we had done maximum likelihood estimation, we would have gotten theta ML equals the relative frequency of heads in this case, which would be 2/3, which is larger than our theta map. So we see that the prior in this case pushes the map estimate more towards the high density region in our prior, so closer to 0.5 in this case. An alternative to maximum a posteriori estimation is to actually compute the posterior. Now, let's look at the normal distribution as an example to exercise that. Well, our ingredients are the same. We have n samples from some normal distribution. The model is, as we said, this normal distribution, which has two parameters, mu and sigma squared. Now, for simplicity, let's assume that the variance is already known. So we only have a single unknown parameter that we treat as a random variable. So theta is equal to just mu. And the likelihood is under the assumption that our data is sampled independently, all from this identical normal distribution. The likelihood is equal to the product from n equals 1 to large n, or sample size, of the normal of this xn given this unknown mu that we're interested in estimating and our known variance. Now we have defined the likelihood model. The missing ingredient in order to do Bayesian inference is to define a suitable prior on this unknown mu. Let's use a normal distribution for that. So we're combining the likelihood with a normal or Gaussian prior over mu. So P of mu is equals to normal of, now evaluated at mu, that has a prior mean, which we call M0, and a prior variance, S0 squared. Now, this is of course the mean and the variance that we assume on the mean value. So this S0 squared is probably smaller than our data variance. Given the likelihood and the prior, our posterior distribution is proportional to, so the probability of mu given the data and this known variance is proportional to the prior times the likelihood. In our example, the prior is a normal distribution and the likelihood is the product over n identical normal distributions. Observe that here we have mu and here we have normal distributions that are over xn. However, if we look at the form of the normal distribution, if you write one of those terms, then let's look at especially about the exponent. That's the only part where actually x appears or the mean appears. Get 1 divided by 2 sigma squared xn minus mu squared. And that is, for simplicity say that it's also normalized. We also have a normalizing constant. And that is identical to, well, 1 divided by z exp of minus 1 divided by 2 sigma squared mu minus xn squared. Because we're taking the squared of this part, these are identical. We are allowed to flip xn and mu because we're squaring it. So another way to write this is to say that this is equal to the normal of mu m0 and s0 squared times the product from n equals 1 through n normal distributions in mu with means that are at xn and variance sigma squared. Now we've done a trick. We basically have shown that the posterior is proportional to the product of n plus 1 normal distributions in mu. And the interesting thing is that the product of 2 or more, in this case n plus 1 normal distributions, will again be proportional to a normal distribution. It will not in general be normalized, so it would not integrate to 1, but it would be up to a multiplicative constant equal to a normal distribution. Now, we know that the posterior distribution will be normalized. So actually this proportional part is enough to infer the original normal distribution. So there will be some normal distribution which has some unknown mu and some unknown sigma squared. So the posterior will be a normal distribution. And the whole trick that we have just done is originally we ignored this expensive to compute normalizing constant, which usually requires solving integrals. But just by arguing that the posterior distribution should be a normal distribution in mu with some unknown mean and an unknown variance is enough to give us a recipe to efficiently compute the posterior and compute the exact posterior. So all that we have to do is to find suitable mu and sigma squared values for this normal distribution. Well, sounds complicated, but we will see that it's quite feasible. So let's just get started and write down the likelihood and the prior and see what we get. So the posterior is proportional to the likelihood times the prior. If we write down the likelihood, that's the product of these n normal distributions. And as we said, it doesn't matter whether we say it's mu minus xn or xn minus mu, because it's a symmetric distribution in the mean and the data because of the squaring, times the prior, which is again some normalizing constant that does not depend on mu, times e to the power of this part here that actually depends on mu. The variable of interest appears only in the exponential part, and there only as minus 1 divided by 2 times the variance of distribution times the variable of interest minus the mean of this normal distribution, and that whole thing squared. If we multiply that out, we always get a quadratic part, we get always a linear part, and then a part that is, so to say, constant additive. And here we get the same. We get a quadratic part, a linear part, and this additive. So the quadratic part will always have a negative sign. The linear part can have an arbitrary sign, so because it depends on the sign of the mean, which we don't know. If the mean is negative, then it would have a negative sign. If the mean is positive, it would have a positive sign. And then we have this constant here. So what we will do is we just ignore all of the constants and derive the coefficients of the linear part and of the quadratic part. We know that the coefficient of the quadratic part will be equal to minus 1 divided by 2 times the variance. Right? If we multiply this out here, we get minus 1 divided by 2 times the variance as a coefficient. What we're interested in finding this unknown variance of the posterior distribution. So if we group all of these quadratic parts here, then any coefficients of this quadratic part will equal to this part here. 1 divided by 2 times 1 divided by the variance. So here we see 1 divided by S0 squared, 1 divided by sigma squared. We have n of those, so we get n divided by sigma squared as coefficient of the quadratic term in mu. And we know that this has to be the variance of the new distribution, so of the posterior distribution. Now we will use this variance of the posterior distribution to find the mean, because if we look at this here, the mean will always appear with a 2 times mu, the variable of interest, times the mean, divided by 2 times the variance. So if we keep the variance here, then we can infer that the mean needs to be this term here. And everything else we just ignore as constants. Now, there will be some additive parts here that do not depend on mu. And, additive constants in an exponential function can always be pulled out. So if we had, say, some plus C4, then we can always remove this C4 here, move it outside as by exponentiating it and multiplying it to this whole term. And that allows us to completely ignore all the terms here that do not depend on mu, because we can arbitrarily move something in. So we could also say we had some C5 here that is multiplicative. We could also move it in by saying it's plus log of C5. And we can arbitrarily do that such that it comes out to be the mean of this new posterior distribution to the squared. And we know that everything that is outside will just be the normalizing constant of the posterior distribution. The trick that we have just done is called completing the squared, which I'm sure you have done for squares in school. In this case, it's a little bit more complicated squares, but in the end, it's not more than just completing a squared, such that we get this form of here something minus the new mean to the squared. Note that all constants were dropped on the way because the evidence just follows implicitly by knowing that the whole thing will be a Gaussian distribution. It's enough to know that there's a Gaussian distribution, and if we have the variance and the mean of this Gaussian distribution, we already know the textbook formula of the Gaussian distribution, which is always normalized. So we took a huge shortcut by knowing that the posterior is a Gaussian. Now if we rewrite these parameters a little bit, then we can look at them a little bit closer. We see that the mu is equal to the variance that we assume to be known divided by n times the variance of the prior distribution over the mean plus the variance of the data plus n times the prior variance divided by n times the prior variance plus the variance of the data times the maximum likelihood estimate. Remember, the maximum likelihood estimate, mu ml, is given by the sample mean. If we realize that the posterior mean is the weighted average between the prior mean and the sample average, then we can look at some limiting cases. So if we don't have any data points, n equals 0, then in that case, the second part here becomes 0 because we get 0 on top here, so 0 times the maximum likelihood estimate, and we get sigma squared divided by sigma squared equals 1 times the prior mean. So without any data, the posterior mean is equal to the prior mean. Makes sense. And if we let n to get very large, so let it go to infinite, then the first term we will essentially divide by a very large number. And in the second term, the fraction will tend towards 1. So in the first case, we're essentially getting a 0 times the prior mean plus 1 times the sample average. So for a large data set, the sample average, which is equal to maximum likelihood estimate, will be equal to the posterior mean. So the frequentist method would yield the same result as the Bayesian method if the dataset is large enough. That is reassuring. Let's look at the posterior variance. 1 divided by the posterior variance is equal to 1 divided by the prior variance plus n, the size of the dataset, divided by the variance of the data. Now if n equals 0, so we don't have any data, then the second term will be equal to 0, and 1 divided by the posterior variance is equal to 1 divided by the prior variance, or the posterior variance is equal to the prior variance. Now if we get a very large data set, so we let n go to infinite, then 1 divided by the posterior variance will go to n, which is going to infinite, divided by the variance of the data, which is a constant. So this will go towards infinity, which means that, well, because we had talked about 1 divided by the posterior variance, which means that if we flip that around, the variance will tend to 0. That means that the more data that we get, the closer to more peaked the posterior distribution will be. And it will be peaked around the posterior mean, which is equal to the maximum likelihood estimate, which is equal to the sample mean. Let's look at the posterior for various sizes of n. So the posterior of the mean, given the data set, and a known variance is, without any data, equal to a prior. So a prior, if we don't know anything about the mean, it's sensible to assume that M0, the prior mean, is equal to 0 with some wide variance. Now, as we observe more data, this posterior distribution moves away from 0 to a new mean. If we observe a second data set, it moves more away from 0, and at the same time it becomes more peaked. And an interesting property is that we don't, for any given dataset size, just have a single estimate for the mean. The map, that would be a single estimate. The maximum likelihood estimate would be a single estimate. But we always keep around a whole distribution of plausible values. So for a dataset of size 10, we would say that the whole red distribution here all would be plausible, say in this range here. The width of this distribution represents our remaining uncertainty. In the estimates that we could get. So the more data that we get, the more this posterior distribution will peak around a single value, which means that we get more and more certain that this is the correct estimate. Now in the Gaussian example, we took a mathematical shortcut by reasoning that the posterior had the functional form of a Gaussian distribution. And then we used completing the squares to find the parameters of this Gaussian distribution. And this shortcut allowed us to not deal with this annoying normalizing constant. Now, the fact that this was possible is actually not a coincidence, because the Gaussian distribution belongs to a class of distributions that has a so-called conjugate prior. So we had the Gaussian likelihood, and the conjugate prior for the mean of a Gaussian distribution is also a Gaussian. A prior is called conjugate for a particular likelihood. So the Gaussian is conjugate prior for a Gaussian likelihood, or the mean of the Gaussian likelihood, if the posterior distribution is of the same functional form as the prior. Our prior on the mean was a Gaussian, our posterior was also a Gaussian. There's a large class of probability distributions for which conjugate priors exists. And this class of distribution is the so-called exponential family. We don't want to go too deep into the exponential family, just know that all distributions that can be written as this one here, as the product of three different terms, a term h that depends on the variable of interest, times a term g that depends on the so-called natural parameters, of this exponential family, times an exponential term. In the Gaussian we have an exponential term, obviously, that is given by the parameter vector transpose times the inner product of the parameter vector and a function u in x. Now this doesn't immediately look similar to the normal distribution. However, we can reformulate the normal distribution by finding appropriate functions h, g, and u such that this matches. And these thetas, for example, so the natural parameters, they're not identical to the normal parameters that we know for the Gaussian. They're not equal to the mean and the variance, but they're rather the mean divided by the variance. And there's a second natural parameter which is given by -1 divided by 2 times the variance. So it's essentially the inverse variance. So we have the mean divided by the variance and the inverse variance as the natural parameters. Then h of x is actually a function that does not necessarily depend on x in this case here. It's just 1 divided by the square root of 2 pi. This function u is given by the first x and x square, so x itself and the square of x, and g is given by -2 times theta 2, so the inverse variance, the square root of this term times the exponent of this variance normalized mean, the first parameter, to the squared, divided by 4 times this -1 divided by 2 times the variance. Once we know that a distribution is a member of the exponential family, so once we have shown that it can be reformulated as the product of these 3 terms, then we know that a conjugate prior exists. There's not necessarily an easy recipe to find it, but all of the commonly used distributions in statistics, except for some weird ones probably, are members of the exponential family, and usually their conjugate priors are known. And you can just go to Wikipedia and, like if you have a Bernoulli distribution and want to look up the conjugate prior, you will see, the conjugate prior is the beta distribution, as we have used in our example before, and so on and so forth. The intuition is that the exponential form of the exponential family ensures that we can construct a prior that keeps the functional form. So the prior itself is also an exponential family that will always have this form. Now for the Gaussian, we already saw the conjugate prior of the mean, which is a Gaussian distribution. Similarly, we could say that the mean is already known and we want to place only a conjugate prior on the variance. That's a so-called inverse gamma distribution, which means that the 1 divided by the variance is gamma distributed. Or we could even find a joint prior distribution over both the mean and the variance of the Gaussian. So we could do full Bayesian inference over both parameters, the mean and the variance, by using the so-called normal inverse gamma distribution, which is essentially the product of a normal distribution in the mean and a gamma distribution in the inverse variance. However, they're not independent. Why not? I mean, that's a product. Why shouldn't they be independent? Well, we have to be a bit careful because the variance of the part that is sort of the prior on the mean actually depends on the variance of the data, which also appears in the inverse gamma part. So they are linked by having sigma squared in both of these terms. So it's really one joint distribution over mu and sigma squared, not the product of two independent distributions. Once we have exponential families and we're working with conjugate priors, we know that if we observe a data set, then the posterior will have the same functional form as the prior. So why not then use this posterior distribution again as the prior if we observe more data? Bayesian inference, in fact, naturally leads itself to sequential learning, where in the beginning you don't know anything about your data, so you just define the prior based on the best of your knowledge about the problem. So what is a sensible value range of a parameter, such as the mean of a Gaussian distribution? Then you observe a data set. You use this so far not very informative prior to compute a posterior, which is, of course, much more informative because it contains information about data, and use that as a prior distribution, because it has the same functional form. It's, again, the conjugate prior of your normal distribution of your likelihood. So we can use it, this posterior distribution, as the prior distribution if we get a new second data set, as long as the data sets are sampled independently and, of course, identically, because we are estimating the parameters of the same distribution. We can do this procedure and always get a new update of this conjugate prior distribution to compute a new posterior that now has absorbed both datasets 1 and dataset 2. In fact, the sequential procedure will yield exactly the same results as if we just created a union of all of these datasets, as long as all of these datasets are independent of each other. So the single-step learning and the sequential learning would yield the same answer. Now let's summarize what we have learned. We've introduced Bayesian inference, where instead of getting a single parameter estimate of, say, the mean of a normal distribution, we actually compute a posterior distribution over these parameters of all possible plausible values. This posterior distribution can be obtained using Bayes' rule, which tells us that the posterior is proportional to the product of the likelihood, the distribution of the data, that is parameterized by the parameter of interest, times a prior distribution over this parameter of interest. So the prior distribution is a distribution over the parameter. We're essentially treating the parameter as a random variable. Of course, if we're fine with just getting a single parameter estimate, and in case it's not easy to actually compute this posterior because it's only proportional to the likelihood times the prior, so we're still missing the normalizing constant, then we could just maximize this proportional distribution in order to get the maximum posteriori estimate. That is a single point estimate. Often, if we work with members of the so-called exponential family, such as the normal distribution, the Bernoulli distribution, and so on, pretty much all the relevant distributions that we used in machine learning and statistics, then we can do efficient updates and efficiently compute the posterior distribution. We have shown this in the example of doing posterior inference over the mean of a Gaussian distribution, and briefly looked at the exponential family. And with this, I want to say thank you and goodbye. See you next time.